It sounds almost too crazy to be true, but tachyons are hypothetical particles that could travel even faster than light. These fascinating particles are currently challenging our physics because they could finally solve the great mystery of dark matter. The way these particles influence and shape the universe challenges the established principles of relativity and forces us to rethink our fundamental concepts of space, time, and causality in a fascinating way. If tachyons really are what scientists think they are, they could mean a revolutionary change in our understanding of matter and energy. These particles are hypothetical particles that theoretically travel faster than light. It was Albert Einstein who showed in his theory of relativity that nothing can actually travel faster than light. If these particles now prove otherwise, they could be the passageway to a whole new dimension of the universe, taking us beyond relativity and its long-held field equations. They could even solve the riddle of dark matter once and for all, and thus explain one of the greatest mysteries of the universe. What are tachyons compared to light? Did you know that Einstein came to the conclusion that nothing can be faster than light? He realized that the speed of light is constant in a vacuum and remains independent of the motion of the observer. This assumption led him to formulate the principle of relativity, which states that the laws of physics are the same in all inertial frames of reference. From these considerations, he concluded that nothing can be faster than light, as this would lead to contradictions. In addition, his energy-mass equivalence showed that infinite energy would be required to accelerate an object to the speed of light. These findings have so far been confirmed by numerous experiments. However, we may now be entering new physical territory where completely different laws apply. Tachyons not only exceed the speed of light, they theoretically even have a limitless speed, as they have no interaction with electromagnetic forces. Tachyon comes from the Greek word tachys, which means fast. The catch with these particles is that they are potentially unmeasurable. How could we measure something that presumably has no mass of its own and no speed that could be determined using conventional methods? The particle accelerator in Geneva shows us that such particles can exist. Here, researchers have already found a number of indications of particles that neither assume a stable form, nor are measurable in any way, nor have a mass. You would be amazed if you knew how many such particles there are. In the subatomic realm, it even appears that this type of building block of matter is much more common than any fixed, determinable quantity. In terms of our reality, this means nothing less than that our material world is not as solid, material, and predictable as we thought. Einstein didn't know everything? Albert Einstein, the great icon of astrophysics and astromathematics, put forward a famous theory of relativity around 100 years ago. For a long time, it was the extended basis of our Newtonian physics. But just as Newton could only describe part of nature and the cosmos in his era, Einstein also only recognized part of it. We can no longer avoid expanding these aspects of our natural science. The evidence that our old theories cannot be entirely correct can be seen everywhere. The James Webb Space Telescope is showing us rows and rows of discoveries that don't fit the old theories, and even Hubble, the old telescope, has shown us galaxies so old that they challenge the framework of our old physics at the time. It's no secret that the old calculations of researchers have long shown some serious weaknesses. In particular, our old formulas failed when it came to explaining the large-scale structures of the universe. Radio telescopes have discovered such gigantic structures in the universe that they span clusters of galaxies and never fit into the picture of objects that Einstein calculated. With our old approaches, we were also unable to explain the expansion of the universe, which is not linear everywhere and is also accelerating. Slowly, the clues are becoming abundantly clear, and it's very likely that the answer to the questions about the nature of our universe can be found in the world of the smallest particles. Where baryons, tachyons, quanta, quarks, and many others can be found, completely different conditions prevail. Particle physics breaks previous principles and challenges our physics due to its unpredictability. Tachyons. Possibility of backwards time travel. What have scientists currently discovered? Researchers Samuel Kramer and Ian Redmount have found a possible explanation for the accelerated expansion of the universe in the data from Type 1a supernovae, and they have discovered even more. Tachyons could in fact finally explain to us the true nature of the mysterious dark matter. Dark matter makes up a large part of the universe and is one of the cornerstones of our cosmology. However, it remains completely invisible and unmeasurable to us. The magical thing about this type of matter is that it exists and has effects, but it does not interact directly with light or electromagnetic forces. Exactly the same is true for tachyons, which make them ideal candidates for dark matter. Their superluminal speeds could explain why dark matter is so difficult to detect and how it influences gravity to shape the motion of galaxies and the structure of the cosmos. So far, it's unclear whether tachyons are really direct building blocks of dark matter or whether they only exist within it. So the question remains as to what exactly these particles could be. Apart from dark matter, tachyons could have unique energetic properties that would be able to generate a completely new type of energy that is also difficult for us to describe or explain by conventional means. However, with such energies, we could, for example, master faster-than-light travel and possibly in the foreseeable future. Beyond this, tachyons could mean profound changes for quantum physics and subsequently change our entire understanding of the nature of matter and time. If tachyons actually exist and can transmit information faster than light, they could lead to scenarios in which cause and effect are reversed, challenging the principle of causality. The principle of causality basically states that every effect has a cause and that it precedes it in time, thereby establishing a certain sequence of events. The mere existence of tachyons would mean that information could be sent into the past, opening up intriguing, if paradoxical, possibilities and making the chain of causality suddenly appear illogical or elevating causality spatially and temporally to multiple dimensions simultaneously. This idea would fit in with another discovery. Researchers used a special research balloon at the South Pole to measure a mysterious stream of neutrinos coming directly from the Earth's interior. One of the few plausible explanations for the stream is a dimension hidden in the Earth's interior in which time actually runs backwards. So tachyons are far more than just an exciting and speculative idea that could explain dark matter. They have the potential to fundamentally overturn our understanding of reality. Unstable states in the quantum field and what they mean for our reality. Imagine particles moving faster than light as they appear in the quantum field. They're as crazy as they are, and despite their instability, they could interpret states that can transform the field in which they exist in a new, more stable state. It sounds paradoxical, but this could be the key to a universal understanding of the field equations. These particles are not just mathematical curiosities. They could actually act as catalysts for dramatic changes in the energetic state of a field. Imagine a field is in a metastable state, and tachyons could cause the field to fall to a lower energy state, potentially allowing for new physical phenomena and states. In quantum field theory, which describes the behavior of particles and fields in the subatomic range, tachyons are absolutely logical as mathematical solutions. The idea of tachyons even stems from the mathematical structure of quantum field theory. They showed physicists that their existence is almost absolutely necessary. This is why researchers first came up with the idea that tachyons could exist. However, these solutions are not uncontroversial, as they call into question the principles of special relativity. But quantum physics does that anyway. It is indisputably real, but absolutely incompatible with Albert Einstein's physics. Although Einstein himself was the first to discover a quantum and even received the Nobel Prize for it, he rejected quantum physics throughout his life due to its unpredictability. One example of the role of tachyons in quantum field theory is their function as unstable states. These unstable states, also known as tachyon condensation, can occur when a field is trapped in a metastable state. Due to the presence of tachyons, this field can transition to a more stable state through the principle of energetic minima. This transition is similar to quanta striving for a state with the lowest possible energy. Tachyons serve as catalysts for such transitions. This would make them elementary building blocks of our reality at a low energy level. They could therefore be related to certain symmetries in physics. Symmetries are fundamental principles that describe the interplay of certain physical quantities under certain transformations. In this exciting context, tachyons could exist as particles that either preserve or break symmetries. Thus, these particles would be basic structures of many, if not all, physical systems and could provide us with the key to symmetry transformations and new insights into the structure of the universe. One particularly fascinating aspect of these symmetry considerations is supersymmetry, a theoretical extension of the standard model of particle physics. Supersymmetry postulates that every known particle has a supersymmetric partner. In this framework, tachyons could appear as supersymmetric partners of ordinary particles and play a crucial role in certain symmetry breaking. This symmetry breaking could reveal more and more new physical dimensions and phenomena that go far beyond our current theories. In quantum field theory and particle physics, symmetry breaking is a mechanism that can give rise to new physical states. If tachyons are involved in such symmetry breaking, they could fundamentally influence the dynamics and structure of fields and particles. This would not only mean that tachyons could explain how certain particle masses are generated, they could also help to understand reality more comprehensively, even manipulate it or create in our world what we previously thought was completely impossible. Subscribe to the channel now and be part of every new video.